All right, so here is the warm-up for today, and it is all about looking at the slope field and identifying the best equation for that slope field. So give it a try. Feel free to send me your answer to check in and see if you've done it correctly, and I will give you some feedback. All right, so we have here a new definition. We're going to be calling any equation that is a differential equation, we're going to call it separable if it can be factored as a function of x times a function of y. So if we look back here, you will notice that this first function, let's see if I can get my marker pulled up, that our first function here, this dy dx is x plus y, is not separable because it's a sum, not a product, but the d is x over y is what we call separable because it can be written as x times 1 over y. All right, so we're going to be taking a look at this specific differentiable equation right here. Differential equation. So we have dy dx is equal to x squared over y squared, and we want to solve it. So the first thing we're going to do is we're going to rewrite it in such a way that the dx goes with the x squared and the dy is with the y squared. Now if you notice here, you'll see that the y squared is mathematically 1 over y squared, and in order to get it to move to the other side, we're going to multiply by y squared. So we get y squared dy on the left. Now similarly, to get this dx to move to the other side, we're going to multiply both sides by dx. And then we get on the right hand side x squared dx. And really this is just some algebraic manipulation in order to get our derivative in terms of y and in terms of x on opposite sides of the equation. We will then integrate both sides. For the left-hand side, we have the integral of y squared dy, and then on the right-hand side, we have the integral of x squared dx, so with respect to x. On the left, we end up with 1/3 y cubed, that's our antiderivative, plus some constant. We're going to call it c sub 1, because there will be multiple constants in this problem. And then on the right-hand side, we have 1/3 x cubed plus some other constant. We'll call it c sub 2. Now, ultimately, our objective is to find a solution y, so we need to solve this equation for y. So I'm going to go ahead and I'm going to move the constants so that there's constants just on one side, and that leaves us with 1/3 y cubed is equal to 1/3 x cubed, and then over here we're going to get this c sub 2 minus c sub 1, and I'm going to call that c. So we're going to let that just be one single constant, because a constant minus a constant is still just a constant. Okay, now we would like to solve this equation for y, so I'm going to multiply everything on both sides by 3. And that's going to leave me with y cubed is equal to x cubed plus 3 times my constant. And then I'm going to cube root both sides of the equation in order to get that y by itself. So I get y is the cube root of x cubed plus 3c. And we would say then at this point, this is our solved differential equation. Now, note that c could be a whole bunch of different possible values, so this is a generic solution. Now, what we want to do is we would like to find, for part B, a specific solution, right? So we are going to take, if I can get this to show up for me, hold on one moment. We are going to take this, I guess I'm writing in highlighter, my computer's being a bit silly. We are going to take this information here and we're going to plug it in. So we get y of 0 is equal to our cube root of 0 cubed plus 3c is equal to 2. We will cube both sides, so we will get 0 plus 3c, which is 3c, is equal to 2 cubed, which is 8. And then we will divide both sides of the equation by 3. So we get that c is 8/3. Now, when we substitute this back in, we get y is the cube root of x cubed plus 3 times 8/3, which is just plus 8. And then this will be our solution for part B. All right, now for our last example, for our second example, we're doing nearly the same thing. So we have here our differential equation, dy dx is equal to 6x squared over 2y plus cosine y. We need this entire piece to go to the other side, the left side, with dy. So we get 2y plus cosine of y dy, and then on the right-hand side, we have 6x squared dx. Just like before, we will integrate both sides. The left-hand side here becomes y squared plus sine of y plus our constant. And then the left-hand side becomes that. The right-hand side becomes, let's see, will become, we're going to divide by 3, so 2x cubed plus some constant. Now, moving the constant to the other side, and then just like before, we have here y squared plus sine y, 2x cubed plus some constant, and we will let our c be just the difference between those constants. Now, at this point, there is no algebraic method to solve this, so we're going to leave this alone, and we're going to say that there is our solution. If we did have a special graphing application we could use at this point, and we could find implicitly a solution. That's it for example 2. All right, our last example. Example 3. A particle moves along a horizontal line so that its acceleration at time t, when time is greater than 0, is given by a of t as 2t plus cosine of t, where t is measured in seconds and a is in meters per second squared. Suppose that the velocity of the particle at time 0 is 3 meters per second, and the position of the particle at time 0 is 4 meters. Find an expression for the position particle at time t. Now, note, we've done this problem before, and it's really quite similar, but we're going to approach it as a separable equation, so a little bit different. So we know that acceleration is mathematically change in velocity over change in time. In other words, a of t is dv dt. And we know that here, that is 2t plus cosine of t. Now, if we treat this as a separable differential equation, we get dv is equal to 2t plus cosine of t dt. Integrating both sides of the equation, this becomes v is equal to t squared plus sine of t plus our constant. Now they tell us in the problem that the velocity at time 0, so v of 0, is 0 squared plus sine of 0 plus c is 3. So we can see that c is 3 and that v of t is just t squared plus sine of t plus 3. Now similarly, we're going to work backwards from velocity to position. We know that our velocity is just the change in position over the change in time, meaning that ds dt is t squared plus sine of t plus 3. And then we will rewrite this as a separable equation as ds is equal to t squared plus sine of t plus 3 dt. Integrating both sides of the equation, this becomes s is equal to 1/3 t cubed minus cosine of t plus 3t plus a constant d. We know, according to the problem, that at time 0, we are at a position of 4. So s of 0, which is 1/3 times 0 cubed minus cosine of 0 plus 3 times 0 plus d is 4. Everything becomes 0 except for the cosine of 0 and d, so this is -1 plus d is 4, or d is 5, and so our position, s of t, is 1/3 t cubed minus cosine of t plus 3t plus 5. And that's that. Here's some practice problems to try. Give it a try.